Let's learn how to write electron configuration. Electron configuration is this weird code that you see up above my head there that tells us where the electrons live around the outside of an atom. Now, why would we ever need to know something like this? Well, here's the thing. If you can predict where the electrons live around the outside of an atom, you can predict how it will interact with other things. So this code, called the electron configuration, is hugely important in our understanding of chemistry. The electron configuration for strontium is on your screen, so you can see that, but you might not entirely know what that means yet, but that's what we're going to learn here together. It is the representation of where the electrons live around the outside of a nucleus. I like to say it shows the address of the location of each electron around the outside. Now, we need to take a step back to an earlier lesson. And if none of this that I'm about to write makes sense to you, then go down to the description down here below in the video and watch those videos before you come back here, because this is going to seem really strange if you don't know what I'm talking about. In our lesson on atomic orbitals, we learned that the s orbital has one shape. It's spherical. 2 electrons can live in that orbital, and it starts at energy level 1. We looked at the p orbital. There were 3 shapes in the p orbital. Each could hold 2 electrons, so that's a max of 6 electrons, and that didn't start till energy level 2. Now, bear with me. We're going to put all these pieces together, and it's going to make sense. Then we looked at d orbitals. All right, the d orbitals had 5 different shapes. Each of those shapes could hold 2 electrons opposing each other. That means there'd be a maximum of 10 electrons living in those d orbital shapes, but that didn't start till energy level 3. And finally, we got to the f orbitals. There were 7 different shapes. Each could hold 2 electrons. That's a total of 14 electrons. Didn't start till energy level 4. All right, let's take this information and start to write electron configuration. The following are the rules for writing the electron configuration in filling order. In my class, I teach high school chemistry. If there's a box on a screen, that's something that you need to write down because it's something you're going to need to come back to quite often to refresh your memory. There are 3 key rules that we need to understand as we start to write electron configuration. The first one is called the off-bow principle. Electrons are going to enter the lowest energy orbital first. What does that mean? I'm going to show you, and we're going to make sense of it. The second rule is the Pauli exclusion principle, which states at most 2 electrons per orbital, and they spin in different directions from each other. And the last one is Hund's rule. Hund's rule states when electrons occupy orbitals of equal energy, they do not pair up until they have to. And that's not going to make any sense until I show you an example. So once you get done writing this down, putting a box around it in your notes, hit the play button, and I'll show you what these mean. So now that you've got the rules, let's take a step back to something we learned earlier. Let's think of these energy levels as a ladder, because if you climb higher up on a ladder and you were to fall off down to the ground, you'd fall down with a lot more energy than if you were on the first rung of the ladder. But this is a little better representation of the ladder. Our nucleus would be here. Electrons can live on these different energy levels, and they can fall down to other energy levels. So if an electron is way out here, it has more energy than an electron that would be living down here closer to the nucleus. This is my ladder, but now I need to represent my ladder this way. There's the first rung of the ladder, the second rung of the ladder, the third. As we get further away from the nucleus, we can see the different orbitals. We can see there's these box things. And let's find out what this really means. This is called the orbital diagram. This is my ladder, right? But this isn't exactly correct. I need to take and I need to adjust my ladder to make it more realistic. So, did you see that? I had to shift all of the p orbitals up a little bit. Here's why. If I look, this is the second energy level, or the second rung of my ladder, okay? Further away from the nucleus where electrons could live. In the s orbital, I can have electrons living there, but apparently if I have electrons that live in the p orbital on the second energy level, they are holding on to more energy than the s, because these are no longer even. Same thing with the third energy level. Those electrons living in the p orbital, I'm going to draw them in here, are going to have more energy. Now I have to do it with the d orbital too. Look at this. I have to shift that way up. And the f orbital, So this is still my ladder. As I get further away from the nucleus up my ladder, I have to have more energy to be further away. But my whole ladder just had to be bent a little bit to truly make it accurate for where electrons live and how we're going to write that weird code. So bear with me, but now my ladder is correct. The other thing is, I highly encourage you to write this down in your notes. I'll have a link down in the description where you can print one of these off that I've made if it's easier to print it off and mark in it like we're about to do. But you can print one off for free, or you can just write this down and work along with me. Now remember, the lowest energy levels are going to fill up with electrons first. The energy levels overlap. All that means is we had to twist our ladder to make it more accurate. We're going to use a counting system. I'll show you what that means. Each box up here is an orbital shape. So we're going to represent that there's electrons living there by writing in those boxes. Each box has room for 2 electrons. In other words, each orbital or suborbital of that shape can hold 2 electrons. If it doesn't make sense, stick with me. I'll show you. We're going to draw electrons this way. Why am I using an arrow? Because if you remember, one of our rules tells us that they spin in opposite directions. So we can show that using the orbital diagram. Now look, this is filled up. It has 2 electrons in the 1s orbital. No more electrons can fit there. So if I wanted to have a third electron show up, it wouldn't be able to live here. Where would it live? Well, it'd have to live at a different energy level. Now, I want to show you this whole process using phosphorus. The first thing we need to do is find phosphorus on the periodic table. There it is. Phosphorus is number 15. That 15 tells us that phosphorus has 15 protons. And if it's electrically neutral, it also would have to have 15 electrons. That means we're going to need to place 15 electrons on our orbital diagram. Here's the best way to think of that. I'm going to use this balloon as my nucleus, and then I'm going to use this racquetball as an electron. Let's say I have a bucket of racquetballs over here. I have 15 of them in there, or 15 electrons. As I throw them at my nucleus, which doesn't have anything around it right now, they're going to land in the spots where they need to be, because that's the 3 rules that we looked at before, tells us where they're going to land. So the first one I throw, well, that's going to end up in the lowest energy level. The next electron we throw at this, well, it's also going to go into the first energy level in the s orbital. So there's the second one. Now that energy level is full. We have 2 electrons right in there close. As I get out my next electron and I throw it at my nucleus, the first energy level is full, so it's going to have to live a little bit further away or in a different energy level. I've used 2 of my 15 electrons. The next one I throw is going to live here, and the next one I throw at this will live here. Okay? I've used a total of 4 electrons. Now, I have to get to 15, so I throw the next one. Where's it going to go? Well, it's just going to go in the next highest energy orbital. So it would go right here. The next one I throw, be careful, it does not go right here because we learned that electrons do not pair up until they have to. So it would live here. And the next one we throw would live here. And the next one we throw, now they have to pair up. And the next one here. Now let's count these up before I go any further. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. And I need to get to 15 electrons. So there's 10. The next one will live here. There's 11. There's 12, 13, 14, 15. Oh, I have to stop there. I've used up all 15 of my electrons. Okay, now why does this matter? You remember at the beginning, I wrote that weird code on the screen that told me where all the electrons lived around the outside of strontium. Well, now we can do that for phosphorus. Let's write it out. In the first energy level, in the s orbital, I have 2 electrons living there. That's where these numbers and letters came from. Then the next place the electrons went to was the second energy level in the s orbital, and there are 2 living there. We kept throwing electrons, right? The next ones ended up in the 2p, the second energy level, in the p orbital, and we had a total of 6 there. 2, 4, 6. We kept throwing electrons. Where did the next ones go? They went into the third energy level in the s orbital, and it looks like we have 2 living there. We kept throwing electrons. Here we go. 3rd energy level, p orbital, 3 electrons. And that's it. This is the electron configuration for phosphorus. Now, if you understand this, if you're following along and you're looking at that and you're saying, I actually think I kind of understand what that means. Well, that's monumental. That's a huge thing because this is a really, really abstract idea that's incredibly challenging for most people to understand. And so if you're following along, maybe it's not perfect, but if you're following along and you're getting this, well, I'm really, really, really proud of you because this is going to be really useful as you're learning chemistry. And I think it's really important that you try these things on your own. So I've got scandium up there as an example. And what I would like you to do is pause the video, draw this out, and see if you can write out the orbital diagram and the electron configuration for scandium. And then come back here and we'll go through it together. But pause the video and try it on your own. That's really the only way to learn. Did you pause the video? Hopefully you did and you tried it on your own. But now I'm going to walk you through it so you can check your answer. I found scandium. It's number 21 on the periodic table, which means it has 21 protons. If it's electrically neutral, it also has to have 21 electrons. So I'm going to take out my bucket of electrons and I'm going to throw them at my scandium nucleus and we're going to see where they land. The first electrons that we throw at our nucleus are going to go in the lowest energy level, so we can fit 2 of them in here. Then we keep throwing, they're going to go to the next energy level that's available. They're going to go here. We keep throwing them. We're going to start to fill up the 2p, but they're not going to pair up until they have to. And then the next ones we throw are going to live here. I've used 2, 4, 6, 8, 10, 12, trying to get to 21, 13, 14, 15, 16, 17, 18, 19, 20. Oh, now we have to be careful. Where's the next one going to go? It's not going to go up here into the 4p. It's going to go here. So look what happened. This 3D energy level filled up after the 4s did. That doesn't seem right because this is part of the 3rd energy level and this is part of the 4th energy. But electrons don't care about our rules. Remember, this is why we had to twist our ladder to make it accurate. The 4s orbital will fill up with electrons before the 3d orbital does. Why? It just has to do with electrons not wanting to be near other electrons, so they'll kind of wiggle in, try to get to the nucleus, but there's other electrons that push them out into other spots, and it gets into all of the dynamics of electrons in the quantum world. All you need to know is that the 4s here filled up before the 3d filled up. Let's write out the electron configuration. That's the order or the filling order, the order that we drew these in, and that gives us electron configuration. We have 1s2. Next one, 2s2. Next one, 2p6. Then 3s2. Then 3p6. Then we filled up 4s2. And then finally 3d1. That is the electron configuration for scandium in filling order, in the order that they would fill up if we threw electrons. Here's the thing, this can be written several different ways. For example, we could start to group it together by energy level, and it's still correct. There are different uses for each way to write it. We have 1s2, 2s2, 2p6, 3s2. This looks exactly the same, but bear with me. 3p6, 3d1. Notice, I grouped them together by energy level, which is totally fine. Just another way to write it. There are other ways to write it as well, and we're going to get into those. It's really important that you can use the orbital diagram to show where electrons live, but there is a more simple way. Here's the trouble. If you try to draw out all those boxes every time you're doing a problem, or maybe you're taking a test or doing a quiz, or maybe you're working in the lab, and you try to draw those out, you have to get them in exactly the right spot every time, or it's not going to work. So there is an easier way to do this for you to write it out and still get it correct every time. That is a bit of a shortcut. So in my class, we still have to be able to write the orbital diagram like we did on the last couple of slides, but I also want you to be able to use this shortcut. This is the ladder that I've been using as an example all the time, saying that as we climb up that ladder, we end up with more energy, because if we were to fall from the top of that ladder down to the ground, it would hurt a lot more. Same thing with electrons. As they get further away from the nucleus, they're holding on to more energy. But look, I'm going to write my ladder this way now. And in my class, it is important that this is memorized. There's no way around it, because you have to be able to write electron configuration all the time. But it's not that hard. This is the first rung of the ladder, and the first energy level only has the s orbital. The second energy level, or the second rung of the ladder, had the s and the p. The third, the s, p, the d. The fourth, f, p, d, f, and all the way up to the top. I like to add a 2 over the top of that column, a 6, a 10, and a 14. That reminds me that the s orbitals each can hold a maximum of 2. The p orbitals can hold a maximum of 6. The d orbitals a maximum of 10. And the f orbitals a maximum of 14. And I recommend you take a moment and write this down in your notes in pen. And then you can use pencil to write on it, because we're going to write all over this. Then you can erase the pencil and you can reuse it over and over and over. I've chosen phosphorus as our first example because we did phosphorus earlier. So I want you to just be able to see how this compares. Like, how do we use this, even though we're going to get to the exact same answer that we got to before? Notice we had to tweak our ladder before, but these ones are all still straight. Like the second energy level's all lined up in the third energy level. So because we're not going to shift our ladder, we're going to have to shift our line. My first 2 electrons can live in this orbital. So I cross it off, and I'm going to put a 2 there to say that 1s2 is holding on to 2 of the 15 electrons. And then I put an arrow here. You don't have to. I like to keep track of how many electrons I've used out of my bucket. Remember, my bucket holds 15 because I need to put 15 on here. So I've used up 2. Now, every line after that is going to be a parallel line to this. So my next line will go right through here. And we know that the 2s can hold 2. And I've used a total of 4 of my 15 electrons. The next line will go right through here, through the 2p and through the 3s. The 2p can hold 6 electrons. The 3s can hold 2 electrons. So that I just added 8 more electrons that I threw at this. I'd already used 4. 4 plus 8 is 12. I have 3 electrons left in my bucket. The next line is going to go right through here. So but I need to pause there, because that 3p orbital, I only have 3 electrons left to put in there. Now here's the thing. Let's write it out in the order that we drew the lines through it. We have 1s2 right here. The next line, 2s2. The next line was 2p6, 2p6. The next one, 3s2. And finally, 3p3. That's the exact same electron configuration we got when we used the boxes in the orbital diagram. But I promise you, this is a quicker way, kind of a shortcut, to be able to write out the electron configuration. The largest element on the periodic table is oganesson, 118. So if it had 118 electrons, this is what its electron configuration would look like. So I just want to show you that, like, the same process that we just did together works for even the largest atom on the periodic table. We're still going. We're up to 88, and finally we get to 118. Now, here's the thing. If that's the largest one, those are never going to get used. I used to teach students not to write those on this diagram. But then I'd have students that would be like, wait, am I supposed to leave the F off on the 5 or the 6, or am I supposed... So to simplify it, we just write it out exactly like you see it, and then you'll never ever get confused, and you'll never ever get any of it wrong. This is a good spot to pause the video and try titanium on your own. So what do? We find titanium on our periodic table, and we see that titanium is number 22. Means it has 22 protons. If it's electrically neutral, it also has 22 electrons. Go ahead and try it out, and then press play, and we'll do it together. Check your answer. Well, hopefully you already gave this one a try. And remember, titanium has 22 electrons. So I'm going to take 22 electrons, put them in my bucket, and I'm going to start throwing them at this nucleus of titanium and seeing where they land. 1s can hold 2. I've used up 2. The 2s can hold 2 more. I've used up 4. The 2p and the 3s, this one can hold 6. This can hold 2. That was 8 more. So 8 more plus the 4 I've already used is 12. We're trying to get to 22. I keep going and I get the 3p and the 4s filled up because this could hold 6 and this could hold 2. That was 8 more. I've already used 12. That's a total of 20. I only have 2 left in my bucket. Where are they going to go? Down here to the 3D, and 2 electrons will live there. Now I've used up all 22. So we write them out in the order that we cross them off. That's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. There is the filling order electron configuration for titanium. Well, you're doing great, but the best way to learn is to try these on your own. So I'm going to encourage you next to go to sodium. Sodium is over here, number 11, has 11 protons, so 11 electrons. If it's neutral, pause the video, try it on your own, and then come back and check. Let's check your answer. 11 electrons for sodium. How many can fit here? 2. I've used up 2. 2 more here. That's a total of 4. I can fit 6 here. Now let's be careful because if I have 6 there and I've already used 4, I've used up 10, right? So as I go to cross this one off, I only have 1 left to put there because 6 plus 1 is 7. And the 4 that I've already used, that means I'm up to 11. So I need to stop there. Let's write it out for sodium. 1s2, 2s2, 2p6, 3s1. Did you get it right? As you saw when we were writing it out for organosin, these can get really, really long. I've chosen ones that were pretty small and simple for our practice ones, so I didn't wear you out right off the bat. But there is a way to shortcut this even more, and it's called noble gas electron configuration. Now, it is really important that you can write out the electron configuration. It's also really important that you can do the orbital diagram, the boxes. But sometimes we just need to be able to shorten this up. And in the next lesson, we're going to learn how to do that with noble gas electron configuration. If you want to learn more things, there's stuff popping up on the screen, lots more down there in the description. Come over and watch some videos of experiments at bealscience.com. And I do all of it just to remind you to keep on learning.